The maximal total range is the distance an aircraft can fly between takeoff and landing, as limited by fuel capacity in powered aircraft, or cross-country speed and environmental conditions in unpowered aircraft. Ferry range means the maximum range the aircraft can fly. This usually means maximum fuel load, optionally with extra fuel tanks and minimum equipment. It refers to transport of aircraft for use on remote location without any passengers or cargo. Combat range is the maximum range the aircraft can fly when carrying ordnance. Combat radius is a related measure based on the maximum distance a warplane can travel from its base of operations, accomplish some objective, and return to its original airfield with minimal reserves. The fuel time limit for powered aircraft is fixed by the fuel load and rate of consumption. When all fuel is consumed, the engines stop and the aircraft will lose its propulsion. For unpowered aircraft, the maximum flight time is variable, limited by available daylight hours, aircraft design, weather conditions, aircraft potential energy, and pilot endurance. The range can be seen as the cross-country ground speed multiplied by the maximum time in the air. The range equation will be derived in this article for propeller and jet aircraft. Derivation. If the total weight of the aircraft at a particular time is equals, where is the zero fuel weight and the weight of the fuel consumption rate per unit time is equal to the rate of change of aircraft weight with distances, where is the speed, so that it follows that the range is obtained from the definite integral below, within the start and finish times respectively and the initial and final aircraft weights. The term is called the specific range. The specific range can now be determined as though the airplane is in quasi-steady state flight. Here, a difference between jet and propeller-driven aircraft has to be noticed. Propeller aircraft with propeller-driven propulsion. The level flight speed at a number of airplane weights from the equilibrium condition has to be noted. To each flight velocity, there corresponds a particular value of propulsive efficiency and specific fuel consumption. The successive engine powers can be found. The corresponding fuel weight flow rates can be computed now. Thrust power is the speed multiplied by the drag, is obtained from the lift-to-drag ratio. The range integral, assuming flight at constant lift-to-drag ratio, becomes to obtain an analytic expression for range. It has to be noted that specific range and fuel weight flow rate can be related to the characteristics of the airplane and propulsion system, if these are constant. Jet propulsion. The range of jet aircraft can be derived likewise. Now, quasi-steady level flight is assumed. The relationship is used. The thrust can now be written as jet engines are characterized by a thrust-specific fuel consumption, so that rate of fuel flow is proportional to drag, rather than power. Using the lift equation, where is the air density, and S the wing area, the specific range is found equal to. Therefore, the range becomes, when cruising at a fixed height, a fixed angle of attack and a constant specific fuel consumption, the range becomes, where the compressibility on the aerodynamic characteristics of the airplane are neglected as the flight speed reduces during the flight. Cruise, climb. For long-range jet operating in the stratosphere, the speed of sound is constant. Hence flying at fixed angle of attack and constant Mach number causes the aircraft to climb, without changing the value of the local speed of sound. In this case, whereas the cruise Mach number and the speed of sound, the range equation reduces to, or, also known as the Breguet range equation after the French aviation pioneer, Breguet.